Hello everyone and welcome to today's lecture in this course of solar photovoltaic system design. And today we are going to talk about the solar radiation resource assessment with a couple of practical examples. So what all we have been learning in the last few lectures, we will be combining everything together and putting it to practical implementation for a couple of case studies. And we will see how we can use the transposition models which we discussed in the previous lectures to estimate the beam, diffused and reflected components of radiation, and thus how to estimate the actual solar radiation incident on the plane of array of a PV panel, which can then be used for assessing the solar PV panel output. So as we know, this course is on solar photovoltaic system design. So there are different aspects of the system design for a solar PV system. So this is the first aspect of system design, that before we install a solar PV plant or we conceive of a solar PV plant, we need to do this assessment of solar radiation resource available at a location. Only when the solar radiation resource is available in good quantity and that can translate into a good amount of electricity generation, then the project will be economically viable, and then we will be going ahead with the large scale solar PV utility scale project. So we will be looking at it from that perspective, how we can use this, all the understanding of the solar radiation which we have gathered in the last few lectures to assess the actual solar radiation resource available at a location. So let us look at a couple of case studies. To begin with, this particular example which I shared with you in the last lecture, in the last slide I gave you this as a practice exercise. So today we will solve this problem step by step and see how we can use our understanding to estimate the solar radiation in the plane of array of a PV panel. So if you go through this particular question, so there is a location shared here given as Roorkee, where IIT Roorkee is located. Latitude is 29.85 degree north, longitude is 77.89 degree east. And we are talking about a particular day at a particular time. So let us say 20th April 2015, 3:15 p.m. time. And we observed that the DNI at that instant in Roorkee was 510 watt per meter square, and the diffused radiation on a horizontal surface was 225 watt per meter square. And now we are assuming that we are taking the tilted PV panel located at the optimal tilt angle. Optimal tilt angle, as we discussed, is the same as the latitude of the location and oriented due south. So module azimuth is 0 degree. So to start solving this problem, the first step, we should write down all the data which is given in the problem. So first thing, we saw that there is this latitude which we indicate by phi in our problem solution which we discussed earlier also. So this angle phi is given as 29.85 degree, and as we discussed in the last class, that we follow the sign convention that all the latitudes in the northern hemisphere are treated as positive angles, southern hemisphere is treated as negative. Then we have the longitude angle given, which is given as 77.89 degree. Again, the standard sign convention globally is that all the longitudes in the eastern half, we treat them as positive, and the western half, west of Greenwich meridian, those are negative. Then the day number, in this case the example we have taken is 20th April. So 31 days in January, then 28 in February, then you have 31 days in March and 20 days in April. So this will be day number 110, D will be 110. The local time or the watch time, clock time at that location as given in the problem is 3:15 p.m. So for this solution you need to convert the time into decimal equivalent. So because it is PM, so 12 noon plus 3 hours, so it will be 15 hours, plus you convert the minutes also into hours. So you have 15 minutes divided by 60 to convert into hours. So the local time at that particular instant is 15.25 hours. DNI is given in the problem as 510 watt per meter square. DHI is also given in the problem as 225 watt per meter square. And as the problem says that we have the optimal tilt angle at that location for our PV system. So optimal tilt angle beta is same as phi, and therefore this will be 29.85 degrees again. And further the problem says that it is due south orientation of the PV panel. So, the module azimuth angle psi will be 0 degree. So, this is all the given information which is already given in the problem. We have converted that into numbers, I mean put it in a mathematical notation here. Now, as we understand the plane of array radiation, we have been talking about it, is beam plus diffused plus reflected. So, we will solve for each of these components one by one. We will begin with the beam radiation first. Now, as we discussed in the last class, the beam radiation is given by this particular equation. However, the interesting thing, as we have been already talking about it, we solved this also in the previous classes, that if you take the standard assumptions or the ideal assumptions in the northern hemisphere, where your optimal tilt angle beta equal to phi and your panel is oriented due south, the optimal orientation which is 0 degree, then this complicated equation gets simplified to this simple equation, B equal to dni cos delta cos HRA. So, we will be using this particular simplified equation in our problem here, because we are having these ideal assumptions in this problem, given problem. So, basically what we need to estimate, dni is already given, we basically need to estimate the delta and the R angle. So, if we estimate these two, then the beam component is done. So, let us do this also step by step. So, delta, as we discussed in the previous lecture, is given by this equation minus 23.45 degree cos of 360 over 365 into d plus 10. In our problem, as we just now noted, d comes out to be 110. So, if you substitute in this equation, you get the value of delta here, and that comes out to be 11.138 degrees. That is the value of delta we get in this particular problem. Then let us solve for the angle HRA. Now, HRA, as you might recall, we discussed that it is not just one straight equation, there are a series of equations we will have to solve. Let us put the equations first in that order. So, the HRA or the R angle is given by this expression 15 degree into LST minus 12. LST is the local solar time, where your local solar time can be obtained from the local time or the watch time by this particular expression, local time plus a time correction by 60. Time correction, as we understand, is given by 4 times the longitude of the location minus the local time meridian LTM plus EOT or equation of time. EOT, which accounts for the eccentricity of Earth's orbit and the axial tilt of the Earth's axis of rotation, that is given by 9.87 sin 2b minus 7.53 cos b minus 1.5 sin b, where this small b is 360 by 365 d minus 81. So, those are the 5 equations which we need to solve to find out the R angle, and as I already discussed that the order of solution should start from the last one going towards the first one. So, in this example we have, as we just now saw, d we have found as 110. So, if you put this value of d in this equation of small b, it gives you the value of small b as 28.6 degrees. So, the solution for b which you get by this equation will always be in degrees, never in radians. So, you have b equal to 28.6. Now, you put this value of b in the upper equation of time, and you get EOT value in this example as 0.968 minutes, which is like almost 1 minute. So, in this example it is coming out as 1 minute, but it is not like always it will be such small value. So, EOT is also important, it is non-trivial. So, as you might recall, in the previous lecture we looked at the graph, the value of EOT can go somewhere between plus minus 15 minutes. So, in this example somehow it is coming out to be small, but not always. Then this we will use the value of longitude given in our problem. This is 77.8 14.89 degree. The local time meridian, because we are talking about India, we understand our standard time meridian from which we derive the Indian standard time, that is 82.5 degrees. And putting these values into the time correction equation and also the EOT value, we will have this expression 4 into 77.89 minus 82.5 plus 0.968. So, our time correction comes out to be minus 17.47 minutes in this example. It will be different under different circumstances, different locations and different days of the year, the value will be different. So, we have minus 17.47 as the time correction. Local time we already saw, we have local time as 15.25 hours at this particular instant, what is given in the problem. So, our local solar time comes out to be 15.25 plus converting the time correction into hours, we have minus 17.47 divided by 60. So, this comes out to be 14.96 hours, and therefore, the R angle HRA is 15 degrees into LST minus 12, and this comes out to be 44.38 degrees. So, we have got our delta and we have got the R angle. So, now we are in a position where we can estimate the beam component of radiation. So, beam component of radiation is DNI 510 in this problem multiplied by cos of the declination angle multiplied by the cos of R angle, and this value comes out to be 357.63 watt per meter square. So, that is the value of the beam component under the given circumstances in this particular problem. So, once we have the beam component, we go for the next components, which is the diffused and reflected radiation one by one. So, diffused radiation, as we understand, is given by DHI multiplied by 180 minus beta divided by 180, because we are taking a isotropic model, as we talked about in the last class. We are assuming a simplifying assumption, we are assuming the diffused radiation to be coming equally from all the directions of the sky. So, in this problem we have DHI as 225, 180 minus beta is 29.85 degrees divided by 180. So, diffused radiation comes out to be 187.69 watt per meter square at this instant. Then we go for the reflected radiation. The reflected component is given by this expression GHI by 2, 1 minus cos beta into the albedo. So, here GHI is not given directly, only DNI and DHI is given in the problem. So, we need to find out the GHI as well. GHI, as we already discussed, is given by DNI into cos of solar zenith angle theta z plus DHI, or the diffused horizontal irradiation. DNI and DHI are given, but theta z we need to estimate. So, first the estimation of solar zenith angle theta z is given by this expression 90 degree minus sine inverse of sine delta sine phi plus cos delta cos phi cos HRA. As we already just now found out, delta in our case is 11.138 degrees, phi is given as 29.85 degrees, and HRA at this instant we found that as 44.38 degrees. So, putting all these three values in the equation for solar zenith angle, we get the solar zenith angle as 45.22 degrees at this particular instant. Now, putting this in the equation of GHI, we have GHI equal to 510 multiplied by cos of 45.22 degrees plus 225, and this comes out to be 584.22 watt per meter square. So, as you can see, GHI at this instant is significantly lesser than just the plain summation of DNI and DHI. So, if you just do the algebraic or the simple plain addition of DNI and DHI, this would be around 735, but due to this cos of solar zenith angle being only 45° at this instant, we are getting this value as 584.22 watt per meter square. Now, putting this value in the equation for reflected radiation, we get R is equal to 584.22 by 2 multiplied by 1 minus cos of 29.85 degrees, and albedo, if there is no specific condition given, then usually for the default value of albedo we take is 0.2. But as we discussed in the previous class, that if a particular type of ground surface is given, then depending upon the ground surface, the albedo value can be different. However, if no other thing is mentioned, like in this example, there is no mention of what type of ground surface is there, then we have this default assumption of albedo being 0.2. And with this value, what we get is this R is only 7.75 watt per meter square. So, finally, our plane of array radiation, which is beam plus diffused plus reflected, we have got beam as 357.63, diffused we have found as 187.69, and reflected we have found as 7.75. So, the total comes out to be 553.07 watt per meter square at that particular instant on that given day at that location. So, the value can be different, in this case, interestingly, it is coming little lesser than the GHI. As you can see, GHI is here and this is there, but it is not a standard thing. So, it will change minute to minute, hour to hour, and location to location, and on the same location also the interrelationship will keep changing depending upon on what day and what particular time of the day we are talking about. So, this is one example to illustrate how we estimate the plane of array radiation. Just to give you a flavor of a slightly different circumstances, because in this case we talked about a location in the northern hemisphere and in the eastern half of the globe, and also we talked about the idealized conditions, idealized orientation and tilt assumptions. So, tilt same as the latitude of the location, orientation as due south. So, let us look at a slightly different problem with a slight different flavor. So, this one process remains exactly the same, but just to give you a feel of a slightly different type of circumstances, I have just changed the location and timing and some other details of in this particular problem, orientation and tilt and all. So, if you see here, we are talking about another location which is Buenos Aires, the capital of Argentina, and the interesting thing is that this is in the southern hemisphere and also in the western half of the globe. So, first and foremost, if we want to write out the data here, the phi or the latitude will indicate it as negative. So, it is minus 34.6 degrees, that is the difference. Longitude here in this case again comes out to be negative, minus 58.4 degrees, because it is in the western hemisphere. Then we have few more things here. So, if you see there is some particular time given 10:30 am. So, that directly you can convert, the local time will be 10.5 hours as we discussed to convert the time into decimal equivalent. But then this UTC minus 3, this is important. So, this gives us the time zone where this location is located. Like India is UTC plus 5.5, we are 5.5 hours ahead of the GMT or the Greenwich Mean Time, also known as the universal time UTC. So, in this case, this location is 3 hours behind the UTC, and if you recall our basic discussion that the earth rotates by 15 degrees in 1 hour. So, if it is 3 hours behind, there is a difference of 3 into 15. So, the local time meridian here would be minus 3 into 15, which will be minus 45 degrees. So, the local time meridian is minus 45 degree in this particular example. Then D, you can calculate the day of the year we are talking about, you can easily calculate it is for 15th May 2016. So, you can take leap year because 2016 is leap year, so February of 29 days. And you can find it out, and DNI and DHI are directly given there. Then a couple of things on the orientation also, if you see. So, here we are saying that the panel is oriented in a different way, it is at 15 degree east of north. So, if you just do a simple analysis, so this is due south, this is due north, east and west. So it says the panel is oriented 15 degree east of north. So somewhere along this direction, that means your panel, the perpendicular to the panel is in that direction, the panel would be facing something like that. Now this is not the ideal orientation for any location in the southern hemisphere, as this is in the southern hemisphere. The ideal orientation would have been due north, facing the equator. But in this example, somehow we are saying it is 15 degree east of north. Now that is very uncharacteristic. Usually any particular PV plant when we install, we will go for the optimal location, optimal orientation. So if I am in the southern hemisphere, I would orient it due north. That would maximize my electricity output. That is a common understanding and very much validated. But why we are orienting here 15 degree east of north? So usually that will never happen in a utility scale PV plant. So when you have a large utility scale PV plant, few megawatts or few hundreds of megawatts, you have a large land area, chunk of land which is almost completely shade free. You remove vegetation or other things, you take it in a location where there is no tree cover, or if there is something, you clear the ground and there are no adjoining buildings or something. So there is no shading coming on the panels. So you just put it at the orientation which is the ideal orientation. If I am in the northern hemisphere, I put it facing due south. If I am in the southern hemisphere, I keep it placing due north. But this type of slight adjustment might be needed for rooftop PV system sometimes. So let's say if you are installing a rooftop PV system and somehow let's say there is some obstruction in the due south direction, and if you orient it due south, there will be shading coming from the taller building or any structure which is in that direction. So maybe just to avoid that shading, you may orient the panel a little differently. So that might be one example why we would do that. Otherwise we wouldn't do that under normal conditions. So in this case we are taking that type of example. We are having 15 degree east of north. Now as we said, we have 0 degree reference as the due south and we measure the angle going from south to west. So the psi here would come out to be 180 plus 15, which is 195 degrees. So we will take psi as 195 degrees. So those are few things we need to be careful about. And another thing is the tilt angle, it is not at the optimal tilt angle. So you have beta equal to 30 degree here, whereas phi is minus 34.6. The optimal condition, optimal tilt in southern hemisphere would be that your beta should be equal to minus phi. So it will be positive in terms of sign, but the magnitude would be same as the latitude of the location. But here we are taking slightly different, maybe due to some error or some mistake, or sometimes the installing agency, the people are not so well trained or they are not very cautious about minor differences. So instead of 34.6 or 35, they have taken a 30 degree tilt, something like that. So under these conditions, so these are like the non-ideal conditions. My psi is not due north or not to 180 degree. My beta is also not same as the latitude of the location. I mean, for this in the southern hemisphere, the ideal orientation would be psi equal to 180 degree. And as you recall, in a previous lecture, we discussed that if you have these two simplifying assumptions, then again your B comes out to be dni cos delta cos HRA. That would be the simplified expression if you have these two conditions, only then. But in this case, none of these are being fulfilled. We don't have beta equal to minus phi, we don't have psi equal to 180 degree. So we need to go for the big equation here. So in this case, we will need to substitute all these values. We will need to find out delta and HRA also. We will take beta and phi as we discussed in the last slide, and the phi latitude of the location is also given. We will put all those things here. It will be a little long expression. So you have 5 different terms and each term is a multiplication of 3, 4 or 5 cosine sine terms. But I mean, it is just, the thing is that you have to be a little patient with putting the values with proper signage. So positive values positive, negative values negative. Take care of the sequence of variables and just be patient with putting the values in a proper way in your calculator or calculating device. And there is no rocket science, you just put the values with proper sign and proper magnitude. And in this case here, interestingly, B comes out to be 358 watt per meter square if you use this long expression. Now, I mean, this is just a simple coincidence that in the previous problem also it was somewhere around 357, here it's around 358, but this is just pure coincidence. It's not like this will be the value always. So in this case, as we saw, dni was 445 watt per meter square and the value came down to 358 under the given circumstances, time and orientation and tilt conditions. And D here, the diffused radiation, that is again the same simple expression, dhi into 180 minus beta by 180, and you will see this comes out to be 287.5 watt per meter square. And the reflected, again you need to estimate the GHI, and then from there you take the albedo. Here again we will take 0.2 because nothing special is mentioned about the ground condition. And the reflected radiation here comes out again interestingly in the same range, 7.32 watt per meter square, like what we had in the previous problem. And then you sum them up, your plane of array radiation comes out to be 652.83 watt per meter square. So as you can see here, the value is significantly different from the previous example. So again, it's just a function of where you are located, what are your latitude and longitude angles, what is the day of the year you are talking about, and what is the time of the day you are talking about. Accordingly, the POA will be calculated depending upon the equations which we discussed. So in this case, we found this value. So these are a couple of examples just to give you an idea or a flavor of how to estimate the plane of array radiation under some given circumstances. But now thing must come to your mind is that we have been talking about just one particular instant in the entire year, but across the year everything will keep changing. So if I want to generalize this, that is important for overall solar radiation resource assessment. So how do we go about generalizing it? So if you see here in this entire exercise, these are two very critical angles which are changing. One is the R angle, another is the declination angle delta. This R angle is having a hourly variation. Every hour the value changes and every day it changes. So there is a hourly variation, and that variation repeats over and over again every day. Whereas delta has a daily variation. On a given day, delta will have one value, next day it will have another value, and like that, so on and so forth. Also, this is a local parameter. So at a given location, the value will be different. At some other location, the value would be different. Whereas this is a global parameter. That means for all the locations on planet Earth, on a given day, the value would be the same for delta. So basically these two are the very critical parameters. And the third one, if you see, which is varying, is, so these are the two varying parameters for beam radiation, right? So the other parameters, if you see, phi is constant, beta, we are taking the standard assumption of fixed tilt panels. So fixed tilt means beta is constant. And so you have phi, you have beta, and the third one here in this equation, as you can see. So delta we talked about HRA, phi, beta, and then psi, module azimuth. So module azimuth also, once you design a particular type of PV system, you decide upon a tilt angle and an orientation angle, then it is constant. So these three are anyways constant. These two are the variables in the beam radiation calculation. In DHI, as we saw, there are only one variable is beta, which is again constant. Then if you look at the reflected component, you need to estimate the GHI. For GHI, another third variable which is varying comes into picture, that is theta z, or the solar zenith angle. And if you recall the equation for solar zenith angle, we just now saw a few slides back, that has got delta, phi and HRA coming into it. So phi is constant, latitude is constant, but then delta goes as an input to zenith angle, HRA also goes as an input to the zenith angle. So what it means is that this will have both hourly as well as daily variation. And again, this is also a local parameter because it is dependent on the phi and the HRA. So basically, if I want to do the overall solar radiation resource assessment, I need to create a code or a program where I'll change these values. So I'll have, let's say, one outer loop for D going from 1 to 365, and then an inner loop for your R going from, you can go from 0 to 24, but usually it's only the sunshine hours which count. And I mean, again, on a location, some places you have the sunshine happening, across the day in particular climatic conditions. And whereas like in India, it's very simple. In India, we usually have the sunshine hours somewhere from 6 AM to 6 PM mostly. So there we will take maybe the R angle calculation only for hours corresponding to clock time of 6 AM to 6 PM. But we understand there are other countries where the conditions are very different, close to the poles or in the Arctic region and all, you have very longer days sometimes very longer nights. So in a general way, we can say we take H equal to overall from 1 to 24. and then in the outer loop I can keep changing my delta, and in the inner loop I keep changing my HRA and theta z, and accordingly I keep calculating in the inner loop, I keep calculating for every R what is the beam, what is the diffuse, what is the reflected radiation, and accordingly what is the plane of array radiation every R, like that. And finally what I can do is that I can make that plot of plane of array radiation. I can have the POA radiation on the y axis in watt per meter square, and the R here going from R number 1 to R number 8760 in the entire year, and there will be some fluctuation, some sort of graph you will get, something you will get depending upon the calculation. And then the total, if I want to find the annual plane of array solar insolation, then that would be the the integral of this plane of array values across the year for R number 1 to 8760. That will give me the annual plane of array solar insolation, which is usually measured in units like kilowatt hour per meter square per year. So that would complete my full solar radiation resource assessment exercise. I have my fluctuation of radiation across the year on an hourly basis, and I have the total solar insolation falling on a unit area at that particular location. So we will not be doing that coding in this course, but I give that to you as a take home problem, and you can try implementing it. I usually give that as an assignment to my students in the class, and they come up with some very interesting results. You can try it for your location, wherever you are located. You can take the latitude and longitude for your location. You can get the DNI and DHI data. There are different online data sets also which are available. One very standard and acceptable data set which I refer to my students for this assignment is, there is this agency in USA known as the National Renewable Energy Laboratory of US. They have provided this one open portal. You can go to this NSRDB, National Solar Radiation Database, NSRDB viewer, and if you go to that particular, there is an online portal, you can search for that in Google. You go to that portal, it opens map of the entire globe. You can zero down to your location, either you can go and locate it, or you can search for your location and it will take you to that location. So you go to your particular location of interest, and then you select what particular type of data set you are interested in. You will see there is a pane on the left hand side where there are different types of data sets which are available, they are given. You go for the TMY data set. So in our case, if you are doing it in India, there will be a particular data set known as South Asia TMY data. So you go for that South Asia TMY data, and then you can select what all variables you need. So you can definitely, you should take DNI, DHI, and even interestingly GHI is given, you do not need to calculate in the data set. And you can also go for temperature, wind speed related parameters, pressure and all, those all things are there. So you can select those different variables, download the file, and then you use this particular, try with just DNI, DHI first, and then you can cross check your results with the actual GHI which is in the model. And then you can find out what is the radiation fluctuation over the year at your place where you are located, and also what is the annual solar insolation at your location of interest. So that would form the first step in the design of the PV plant. So this completes our first section or the first unit of this course, and which focused mainly on the solar radiation resource assessment. From the next lecture, we will be starting the second section of this course, where we will be looking at the solar cell in much more detail. Thank you.